Hello everyone, welcome to another topic webinar. Today we'll be hearing from Dr. Maxime Siegler from Johns Hopkins University. Just before we get started, I'll just make some quick announcements. So firstly, please do feel free to ask questions throughout the webinar. You'll be able to use the Q&A button at the bottom of your screen to do so, and you'll be able to upvote questions that have been asked by others already. I will ask the questions at the end of the webinar. So you have plenty of time to ask them. We expect to be about 30 minutes today, just to give you an idea. Please do join our X-ray forum. So there's a QR code here you can scan to go there. If you're not a member already, it's a very useful resource where we have lots of information about how to use our systems and software and so on. So that's all I wanted to say. Now I'd like to pass over to Dr. Maxime Siegler. So Maxime is at Johns Hopkins University in Baltimore in the United States. He has been a good customer of ours. So he's had an XtaLAB system, a supernova system, and now a Synergy-R. And today he's going to tell us about his experiences of using the Synergy-R. So Maxime, please take it away when you're ready.
Thank you, Fraser, for the introduction. I'll take the lead. Let me just share the screen. All right, everything is good?
Yes, I can see.
I don't see the other. I had it before Zoom. I can't see my. Oops. How do I go to the Nope, I don't see my slides, sadly. Do you see it?
I can see your PowerPoint screen, yes. It's not in presentation mode just now.
Trying to. Can you see it now?
Yes, that's fine. Yeah, perfect.
Okay, all right. I just don't see the whole Zoom thing, but that's okay. All right, thank you for the introduction, Fraser. My pleasure to be here. We'll, as you mentioned, I will show for the next 30 minutes. I will explain my experience with the Rigaku Synergy-R and how I came from a supernova to Synergy-R. And this slide, the first slide, and I won't talk too much about these samples. I have so many samples, but this one was a tough one. As you can see on the slide here, let me just turn on the pointer if I can. Laser pointer. Here we go. So this is the 0KL precision photographs, and that crystal didn't diffract at all in supernova. And I just was lucky to find one crystal, and they're not easy. Hard to see from the loop here, but as you can see from the crystal dimensions, one of them is very thin, and those are kind of plate that bend very easily, very flexible, and they don't generally diffract well. Supernova, almost nothing. On the Synergy-R, I was able to find one crystal that diffract okay to 0.86 angstrom in terms of maximum resolution. Diffract nicely single, a fairly long data collection time, about 15 hours, 10 seconds for the low theta scan, 30 seconds for the high theta scan, and we were able to get that structure. In this case, the actual ligands of this ruthenium complex are very loose, and in terms of crystal backing, it's not very optimal. There's a lot of like salt molecules in the crystal lattice. So, but very happy to get that. With super synergy, with supernova, impossible to get that. Anyway, we'll move on. So just a brief introduction for my lab. For about, so I used to have, Fraser mentioned that I used to have an XtaLAB 3. My predecessor got that in 2003, I think, and I took the job in 2009. So I was still able to use that XtaLAB 3 until mostly like when the supernova arrived in early 2013. And it was used first as an owner. It was a demo site that we later purchased from Agilent Technology, which was later purchased by Rigaku. This instrument has been great. Both it's a dual source moly copper, as you can as mentioned here. About 3,400 data sets has been collected so far. It's still running. Both copper and moly still run nicely. Very happy. But of course, there's some limitations, which I will explain in the next slide. As of now, mostly used for like solid-state chemistry, mostly inorganic, from physics or from chemistry, solid-state materials that those guys do. That generally tend to diffract fairly well. So with a moly source, no problem at all. I also use this as for my teaching, for my class when I teach the X-ray course, and so that really provide a good hands-on experience on the with the students on these instruments. And of course, it can be used as a backup as well in case that our main workhouse, the Rigaku Synergy-R, will be down, and sometimes, and I will explain. So the Rigaku Synergy-R has been the new instrument. I only use copper. I know there's a DW version which has both moly and copper, but for what we do, I think the copper source is just, it's been superb, to be honest, and it tackles most of what we want to do, and it makes things much easier in some ways. So I thought the copper source will be easier to justify when I apply for the NIH grant. So we got that instrument thanks to NIH. We got the instrument via grant and in 2002. So it took about a year to get to get the money, and then eventually get the installed and everything. So it was installed in May 2023. I have collected so far 450 data sets, and still very fast, very beautiful data. I will show some in the next few slides. Definitely, as I mentioned before, like it really tackles many types of samples, from small molecules to proteins. If that's what you're looking for, this Rigaku Synergy-R is a Formula One, to be honest, is a beast. Great. Really, if I had to summarize that the instruments, they combine speeds and productivity, is just a super package. All right, so the transition from supernova to Synergy-R, and the gap is fairly big in terms of flux, X-ray flux, and detector. Everything is just a huge update over it. And so from a supernova, I mentioned that even though I collected a lot of data set with supernova, there's been always my main frustration was always like the inability to tackle some challenging samples, which tends to be most of the time the important ones. So when I wrote the NIH grant proposal, I have in my mind three types of three classes of samples that I could not tackle very well, or if not at all, with a supernova. And the first two, which we will mostly focus today on, are tiny crystals, samples, especially with low light atoms, which have very small crystal dimensions, let's say 10 to 20 microns, 40 microns, but 10 to 20 microns, let's say. This is just like no way that you can get that with the on the supernova, unless maybe if you have like very like inorganic solid materials, and just like, but most of the crystal will not diffract at all. So this was always one of the bottlenecks that I had with supernova, was just like not tackle small crystals. And sometimes, most of the time actually, like important compounds down to crystallize in fairly small size. Also, number two, the difficult samples, the diffract poorly. So if you have a lot of disorder in the crystal lattice, also if crystals contain quite a bit of solvent, amount of solvents like MOF or even supramolecular assemblies, that will be very also difficult to tackle those samples with a supernova. So that was quite, having having a very strong X-ray source is critical for collecting data on such samples. And also something that I will not talk today, but keep in mind that we also use, we collect data here at, for proteins as well, especially that the med school now has shut down the X-ray lab. So we are receiving some samples from proteins, but everything that you want to collect when you have like a very long unit cell axis. The problem with the supernova was the beam divergence, which was not, you could not change that, and it was about 4.5 millirads. So it was quite limited. And once you have a long axis or longer axis, let's say 150 angstrom or longer, it's a bit more, it's more difficult to basically have spatial resolution along the scrolls axis because reflections are way too close to each other. So you get overlap and not very good data. So having the ability to change with Synergy-R, sorry, you have the ability to change the beam divergence, and you will get much better spatial resolution along the longest scroll axis, and you will be able to get a much more accurate values of the intensities along these directions. So yeah, those 3 points were really important, and from supernova to Synergy-R, this will provide an answer, at least for like 80 or 90% of the time, that will be successful. So there's a lot of text here. I will just give you a quick summary of this. When it comes to, and please correct me, Fraser, if I'm wrong, but when it comes to technical improvements from supernova to Synergy-R, in terms of flux intensity, from supernova to Synergy-R, you get about 15-20 times more flux. So there's just no comparison whatsoever once you tackle samples on the supernova versus tackling samples on a Synergy-R. When it comes to beam conditioning, I mentioned that the Synergy-R is equipped with a beam sleeve, so you can really change you can change the slit width of a beam, so you can go from 1 millirad to 10 millirad with Synergy-R, which helps tremendously when you want to tackle, especially for protein crystals. Bear in mind that once you minimize the slit width, you will also minimize the X-ray flux as well. So it will run a less, it will be less intense if you use at 1 millirad versus 10 millirad. But still very good options to have when you want to tackle samples which have very long unit cell axis. You have the HPEX detector, just no comparison between the Atlas that I had, and it's the original one versus the detector. You have way more sensitive, barely any noise, noise-free detector, and you can really, the big thing was just you can really collect the data with crystal to detector distance of 34 millimeters, maybe 33 at the best maybe, and that's just really nice to have that, because you really like enhanced, you get a better intensity at when you have a shorter crystal to detector distance, and you can collect data a little bit faster too, because you will have more reflections per frame. And of course, the whole package comes with shorter operations, which makes data collections faster. So all those 4 points suggest that you have like a huge gap between, a huge technical gap between the supernova versus the Synergy-R. Okay, so in the main block of this presentation, I'm gonna mention briefly 5 different samples for which I've been lucky to use the Synergy-R, and I can tackle things that I could probably not tackle the way I would like with supernova. And so sample 1, 2, 3, 4, and 5. Sample 1 is an example of tiny crystals. Sample 2 is a crystal which has actually a very high linear absorption coefficient. When you won't think that you will collect data with copper radiation, but still you can do it when you have a very tiny crystal. Sample 3, that is a big one. This is a microcycle oligofuran with a high Z prime number. That's something that a group from Carnegie Mellon University have been working for years, several years actually, and they could not get anything out of it. And I was able to get the structure of that. Sample 4 is an example of radiation damage. I will explain a little bit. I will show you an example. And sample 5 is a gold copper cluster, nanocluster, which has fairly large number of atoms and still does a very good job. All right, so let's get started. So this is the group from Maxime Siegler from Johns Hopkins University in the chemical engineering department. And they were looking at making some, encapsulating some organic molecules in the alpha cage of the zeolite A-type. And they are like, they do have large crystals, but in this case, we were very interested in looking at very small crystals. And when you're looking at is the SEM picture of the cubes, which look like about the crystals, which are basically like cube-like in terms of morphology, and they're about 10 microns in size, which is fairly small. And what we're interested in is there's two cases. We're just looking at trying first to do the chemical reaction where they insert the organic molecules, and then in case 2, sorry, they were cranking up the temperature. So we're doing some calcination at 700 degrees Celsius, trying to get rid of everything in the cage. And so we wanted to know, to compare it, the structure of case 1 and case 2. So this is what we have done. So in this case, I use, for most of the thing, I use mostly loops, broken loops or good loops. You can see here. And the crystal is this tiny little dot. I zoom in just to show you. So this is the crystal which has the organic molecule encapsulation. And that's the organic molecule that we're looking at. And then so those are not the same crystals, okay? They're from a batch that was done without calcination and then after calcination, but roughly about the same size, okay? And you can see the size are given in the frame. The data were collected at 110 Kelvin. The main difference when you look at those crystals after calcination, they look more opaque. Probably hard to see from this frame, but when you look under a microscope, you can see that they're more like they have lost the reflection of the light a little bit more, so they're less transparent. Okay, so this is a case where most of the time the crystal dimensions about between 10 and 20. Of course, this is like difficult to assess exactly the precise because they're so small. So when you start to make that crystal morphology in Crystallis Pro, it's probably a little bit, like it's not exactly 16 probably microns, but it's between 10 and 20 microns, and so it's fairly small. With supernova, you will probably get nothing out of it. So with Synergy-R, I collected data sets fairly like not super short because they're small crystal, but still nicely. Then you get the one which I've inserted a molecule in the, so this is the beta cage, that's the D4R. There's a fluoride inside the D4R. This is, so during synthesis, they use also TMA hydroxide, so trimethyl ammonium hydroxide. This is where there's in the beta cage here of the zeolite. That's this is the D4R cage, which is the fluoride here. The beta cage, which has the tetramethyl ammonium cation, and then the alpha cage. Of course, when you refine the structure, there's a lot of, so this is the crystallographic data after doing the squeeze refinement. And in the squeeze refinements, so the D4R and the beta cage are occupied, so there's nothing. So mostly it's concerned with all the alpha cage, and this a squeeze volume of about 670 cubic angstrom with about 203 electrons, which is about roughly 1.9 of the organic molecule inserted within the cage. Of course, this is extremely disordered in the cages, so it's very difficult to assess, to make a model of it. But clearly there's some electron density, and it's not insignificant. And now I looked also at the after calcination of crystals, so which is this data set. This is the non-squeeze refinement, but I did also the squeeze just to make sure. So after non-squeeze refinement, there's basically no electron density left in the D4R. So all the D4R cage, the beta cage, and the alpha cage are gone. And yes, and then you basically have only 18 electrons left when you do the squeeze refinement. Basically, like, really shows that the calcination process has been successful, and there's no real organic molecule left within the cage, within the alpha cage. Okay. So this is done on the small crystals, and roughly data collection time is about 4 hours to 5.5 hours. Okay. That shows, this is a very quick frame. This is those of the high theta. So this is the high theta settings. Not sure if you see it, but this is 1.44 angstrom up to 0.79. You can see, even though it's weak, you can still see the intensities around 0.81 angstrom for both samples very nicely. This is done with 20 seconds exposure time at high angle and 15 seconds time. So collecting data with that kind of samples, yes, you can do it with Synergy-R, and that was what we were looking for. Now, this is another one. This is something that you would not think, collecting data on a Synergy-R, but when I got that sample, basically made of potassium, copper, tellurium, and oxygen, so pure inorganic solid materials, and there's also an hydroxide, which I cannot see the hydrogen, but for now it's just beyond the scope of this talk. We're able to get the structure of this samples. The first thing that I've done when I collected, when I looked at the crystal in the microscope, very, very thin needles, and this is a broken loop here, and there's a tiny crystal there, very thin. It's a needle-like crystal, about 10 microns on each side, and then there's a long one. And you would not think to collect data because obviously you have a very high linear absorption coefficient here with that kind of materials, but I still collected it the first time, and it took about an hour to collect data set. The value over sigma is pretty nice. Refound went very well, as you can see. Really nothing problematic collecting data set. So in about an hour, you get a full data set with very high redundant data, about 10 times. Limited, of course, with your resolution of so about 0.81 angstrom in this case, but you still get a very good structure of these materials. Then I got interested and I just say, okay, I'm gonna mount the same crystals on the supernova. And I did the same thing. You get a better, about, I think it was 0.7 angstrom in terms of maximum resolution. But you can clearly see the difference here. Takes 1 hour versus 8 hours and 23 minutes. So 8 times. The I over sigma is nowhere near as good. Obviously, the mu will be attenuated when you use a moly. But it really shows that if you really want to have a quick data set and see what it is, you can get it with Synergy-R very well. And don't be scared to use it with copper, because you can actually do a very good job, especially with small crystals. You don't want to do that with large crystals due to the absorption, which will be too massive. But with very small crystals of 10 microns on that kind of materials, that will work. So that really shows one example, and just want to show you as a side comparison. You're looking at a supernova image with collected on the Atlas generation 1. 40 watt. This is a 20 seconds frame. That's a 1.5 seconds frame on the Synergy-R IPEX with 1.2 kilowatts. So really, you can clearly see the alpha 1 and alpha 2 here. The split, high resolution with copper, but really, like, it makes you can see 1.5 versus 20 seconds. That's self-explanatory here in this case. Sample 3, I think this is the biggest one for me that I've done the Synergy-R. I will say that because this is something from the Carnegie Mellon folks from the group of Noonan, and they have been working for years on this to get that structure. And when they sent me the crystal, the crystal looks actually really nice, very large, red, beautiful, large crystal. Didn't diffract at all. Even with the Synergy-R, it didn't diffract at all. It was going to 1 point. I mean, this is a 1 second frame, but if you increase the frame, first of all, you already see some diffuse scattering, but also it just like dramatically drop in terms of scattering power. So maximum you will get is 1.4 angstrom. So the only thing that they were able to get, it was that unit cells, which seems to suggest either trigonal or hexagonal cell. Yes, and this was collected to 246 Kelvin, and I will explain why. I got interested in this, and I just say, okay, the crystal looks really nice at room temperature, and when I flash cool the crystal, diffraction is about the same as this at 110 Kelvin. So I've tried. I decide just like, okay, I'm gonna do a slow cooling. I do have on the CryoStream 1000, you can really have a very nice control over the cooling. And so I decided to do this, and I went down very slowly. And I noticed a change in the diffraction pattern, very much better diffraction when I was slowly cooling down. So so when you take a crystal and when you just flash cool a fast cooling rate, with a fast cooling rate, you will get basically a low resolution. You will not get a regular resolution. After many attempts, I was able to find that between 250K and 230K, it goes from a trigonal hexagonal phase, which I don't know which because I didn't solve the structure on this one, because the resolution was really poor. I was able to get a triclinic phase, which is twin. And so I was doing a cooling rate of minus 20K per hour, and I know that there's probably a phase transition. They found out after running a DSC experiment that they actually had a small phase transition happening within this range. And then I slowly cooled down to collect to go to 110 Kelvin, get the same triclinic phase at 230K, collect that set. I got a maximum resolution of about 0.84 angstrom, which is a massive improvement over what we were able to get. It turns out that, as I mentioned, this phase is actually twin, but it's surprisingly very ordered. And this is the unit cell, triclinic cell that I got at 110 Kelvin. The structures is solved in the P1 because the side chains have the S configuration. And you get 6 molecules per unit cell. So just to show you, so remember when we look at this is at 246K, no diffraction, basically at 1.4 angstrom, 1.5, 1.6, nothing else. This is at 2 seconds exposure time, and it diffracts way beyond 1 angstrom. This is a good sign, and that was done at 110 Kelvin. The high theta scan at 8 seconds, which is not very much. You can get 1.83 angstrom quite well. And so we're able to get, I was able to get the structure of this, and it looks like 6 molecules. This is view down A, and view down B, you have 6 of those molecules. Surprisingly, as I mentioned, this structure is quite ordered, which is nice. There's about 5-6 side chains which are disordered, which were tackled pretty. So this is a crystal, not too big, not too small. I mean, nothing crazy, mostly like a laugh. So this is one of the 6 formula units. Okay, and I was able to get about 99% in P1 in completeness, and about an R factor of like 8.7%, which is fairly nice comparatively to what we're able to think to get before, which basically was nothing. So you may want to question why I did 2 and 8 seconds. I'm aware that there's like, and I didn't explain to you in the next sample, I will explain to you why, because of radiation damage. And I was wondering if I just do like a very long data set, I will damage the crystals with that. And I only had one shot, so I decided to do it in 8 seconds, which turned out to be okay actually. So that was a good thing. I'm gonna go to the next sample now. So this sample, so I did 2 trials on this, and I was able to get that structure of that tricyclic silane. One trial was done at 1.2 kilowatt. That's a small needle. Diffracts okay on the Synergy-R. I didn't try on the I didn't try on the supernova at all, but I will think that probably it wouldn't work in that kind of samples. And a trial 2, which was done at 480 watts, with larger crystals, and I will explain why. So when I did the trial 1, when I look at the high theta scans, beautiful diffraction at 20 minutes. And I noticed that after about an hour of data collections, things starts to not be so good. And the diffraction was at higher resolution, especially. You can see mostly radiation damage occurring pretty fast at higher theta settings, and you will see the crystals not diffracting well. And so this is a frame at 20 minutes. There's just 120 minutes, same crystal during data collection, and you can see that over time, diffraction is decaying at a very fast rate. And in this case, I think it was about an hour, but some crystal suffer from radiation damage much faster than that. So I just decided to stop the data collection. I was not able to get anyway completeness of 100%, only 66% at 0.81 angstrom. So it was a disappointment, but you know, it happens. So I decided to just crank down the power from 1.2 kilowatt to 480. So basically a 40% power of a full beam. And in this case, obviously, you get the crystal didn't diffract as good because it's you're losing power, but it diffracts. You can see some weak reflections at passing actually 0.8 angstrom after 30 minutes, and then after 420 minutes, you can still see the reflections, okay? So that tells me that at 40%, and those are 15 seconds exposure time, at 40% power settings, you can still have diffraction after 7 hours of data collections. And in this case, I was able to get a 99.7% completeness on P1 bar at a maximum resolution of 0.87, the one very weak at the end. Past 1.81 angstrom is just 1.86 angstrom. The int is really too high to include those reflections, at least to me. So 0.86 angstrom is fine with me when it comes to make sure that this is the right structure. So this is a structure that I was able to get. And as you can see, the I over sigma is not really large, about 3.5, 100 more than 3.5. Took about 8 hours to collect data set, but I was able to get a fairly decent data set, refines to about 5.9%. So that was a success somehow. I don't think these samples will have diffracted at all with supernova. I'm not even sure we'll have diffracted on the Synergy-R, but that's something I don't know exactly. I don't know for sure. Supernova, I'm sure they will not diffracted. The last samples, that's something that so I mentioned here, this is a 48 watts. So this is a mixed gold copper nanoparticles, which has about this, which has the this formula, chemical formula. So notice that the gold is not full. Some of the gold are not fully occupied, but in this case of the drawing, I just make sure that it's gold 13 and copper 5, gold mix gold copper cluster. But that's the real chemical formula, where few gold metal centers are not fully occupied, and they probably have the mixed with the copper. This is a data set where what's collected at 40 watts. The reason why is because I'm very aware that with that kind of compounds, they don't do very well at 1.2 kilowatts. And after generally 20-30 minutes, they decay. So you get also radiation damage. So knowing that from experience, I just tend to automatically go down in power settings to make sure that there's no significant radiation damage throughout the data collections. I'm running a bit late, sorry. So this is the structure has been solved in P22121. They use, I cannot explain too much about the chemistry here because that's first, it's not been published, but they use the RBNAP and they use this ligand to have that metal cluster, and they are looking at structure property of that kind of materials. Crystals was not super big either. Diffracts beautifully at 480 watts. Beautiful structure crystallographic data set, 4.1%. So those kind of crystals contains a lot of sound molecules as well. So just to let you know, so you can see the squeezer found underneath. Not too much. I don't want to explain too much about this. You can ask later if you want to. But just to show you the diffraction pattern, this is the 0KL precision photograph done with the IPX 6000, and you get really nice, very high resolution data set. And this is a frame exposure time of 6 seconds at 40 watts, and you can have diffraction past 0.8 angstrom very, very nicely. Now, if you do that at 1.2 kilowatt, I'll guarantee you after 20 minutes, this diffraction will be gone. So that's the thing always to keep in mind. That's be aware of the radiation damage, and you will learn from experience after like about a year. Once you tackle many different types of samples, you will probably know what type of samples will not do well at full power. But really no big deal, because at 4, if you just go down in terms of like power settings, and you do like trial and errors, eventually you will find the right amount of power that will allow you to collect a full data set, complete data set with high real data and no significant radiation damage. All right, sorry for it took a little bit long, but there's a little bit more things to talk about. I'm gonna just summarize. So with this, the Synergy-R is just really about, that instrument is all about speed and versatility. When it comes to when I'm using copper radiation, I can do a lot of samples. You get way more X-ray flux hitting on the X-ray intensity on the crystal, and it's wonderful. So if you collect a very straightforward crystals, you can solve the structure in 2 or 3 minutes. If that's what you want, great. If that's not what you want, you change right away. I've collected the data set in 10-20 minutes with real data of like 6, 8, which is plenty at 0.81 angstrom to get very good quality data set. The ability of collecting data at tiny crystals is massive for what we do. That's the thing, is that you can or you cannot do it, but once you have that kind of instrument, you can do it, and that's the key. Really works nicely for really crystal, which has a lot of like large molecules, more than 100, 200 carbon atoms. That's really nice to have that. Proteins as well, which I didn't explain, I didn't show because I don't have the time, and I collected 5-6 data set on this. Now, mostly we are doing small molecules in this lab, but I will expect to have more protein crystals during the next year or so. Roughly, I have about less than 10% of received crystalline materials that I reject, mostly because we are not crystal, or we just doesn't not very like good long range order that doesn't allow to collect data set. But I don't think those crystals will diffract with anything. When it comes to another plus is really the Synergy-R has been very reliable. The durable design. I was skeptical, when you have a copper, when you have a rotating anode, but really like the experience has been really good in my case. I think Rigaku has a lot of experience. I've acquired a lot of experience with anodes, so nothing to worry about, to be honest. Surprisingly low maintenance. The anode rebuilt, you have to do like maybe like once 1.5 year time a year. So you have to wait like maybe like 1 time a year, or maybe like you have to wait 1.5 year to change to rebuild the anode. It's about 1 to 2 weeks downtime, sending the anode in and come back, and then you have to install and then do the beam alignment. I would say roughly 8 to 10 days. film on change. So I only changed one time and it lasted for a year. Not sure if I got a very good one, but that's I think normally film on change you expect to change it probably every 4 or 5 months, depending on the usage time. But for me, it was just like it was very easy to do. It takes about a day because you have to realign the beam after that as well. In terms of drawbacks, which I don't explain too much, but really like keep in mind radiation damage of your samples. My experience is about 10 to 50% of the sample that I receive tends to suffer from radiation damage. It can be sometimes not so significant, so that allows you to collect a full data set and you're still okay. But sometimes it's very significant, and then you have to find a different way. So there's 2 ways: either you lower settings, the power settings, or you just change the beam, the slit, the width of the slit. So the width of the beam, sorry, by using a slit. So that can do that as well. One thing that I didn't mention, but that Synergy-R, depending on how you get you water, you chilling water, tends to generate quite a bit of heat. The chiller is about 4 kilowatts of heat, so make sure your room is properly cooled, because otherwise it's going to get very hot. That's something that's very important to have to bear in mind. But other than that, I think that the Synergy-R has been quite superb for what we're doing, and I'm expecting to collect way more data set in the future. So thanks for the acknowledgement for all those guys that have been working, sending me samples, and it's just a small overview of what they did, but it's been great. And of course, thank you for ANH, because without that, I would not get that Synergy-R. So it's been a very good experience so far. And thank you for the invitation, by the way.
Okay, thank you very much, Maxime. So we do have a few questions. Before we answer those, I just wanted to pick up on something that you said earlier on, where you said, correct me if I'm wrong. I didn't want to interrupt your flow, but I did want to just give some context. You said supernova to Synergy-R, you see, you expect, was it 15 to 20 times you said?
Yeah, it's probably more than that, but
yeah. So this is what you said is technically correct. I just wanted to say that the factor is more in the order of 30 to 40 times, depending on the sample size. There's a few factors that go into that. So the beam size is smaller on the Synergy-R. So if you're looking at smaller crystals, it's more suited. And also you're generating quite a lot more photons with the source itself.
Yeah.
You're then capturing with optics. So it's quite difficult to do an apples to apples comparison, but generally speaking, it's around 30 to 40 times from that generation of microfocus source. Okay, so let's go to the questions. So I like the way this question was phrased. This is from David B, and it says, with a super powerful machine from Rigaku, is it a big sin to refuse samples from the users? Or can you still find a good argument to stop and give up? I guess I don't want my life to be too difficult having too many samples to run.
Oh, but for me, it's the opposite. I love it. So it's like so fast, just like the flow, the productivity. If you have to remember, if there's one name that I will say, it's productivity, is just change. It makes your life so easier, because in some ways, in a few minutes you get the structure. So you just like shoot an email to the guy, to the user, and say, this is what you want, this is not what you want. That's it. I love helping people, so for me it's just like this is the right tool for what I do.
Okay. So the next question.
I don't refuse sample. I embrace people sending me small samples.
Okay, the next question. So you use the power settings of the source to reduce the intensity. Have you considered using the divergence slit to do the same thing?
So yeah, you can do that, but on the other hand, you're gonna run. So that will make sense if you have a very long unit cell access. But when you have, for instance, if you use a protein, or if you have like a very long, like a 50 or 60 angstrom, which is not common among small molecules, it can happen, but it's not common. I prefer to use the lower setting, because you're basically using you generate less heat when it comes to the with the chiller. Whereas when you use full power, your chiller is going to get hot. But you can do both. I mean, I've not tried actually with a slip. I prefer to lower the power, so to put less strains on the system and still collect data set. But normally, I think technically you should have the same kind of data set. You will probably get better data set with maybe with a slip with the slit to be a little bit to change the beam divergence to be a little bit smaller because you would have more refined peaks. But when it comes to like a 20, 30 angstrom or even 40 angstrom, it doesn't really matter with copper because you will get a spatial resolution along the reflections along the longest riscal axis will be the shortest riscal axis, which was the longest axis will be fairly well spaced. So either way you can do it, you know. But you put more strains when you use 1.2 kilowatt. You definitely put more stress on the system. It's up to you.
So the next question is related from Bernhard. So he's asking, when you changed the power, how did you change the power? What were the kV and milliamp settings?
I didn't understand the last part.
How did you change the power? Did you just reduce the milliamps on this?
Yeah.
So you left
40,
KV at 40. Or
yeah, the kV is I think by default is at 40K, right? 40K kV.
Yeah.
And then you use like 12, I think, milliamps for 480.
Right, exactly. Yeah.
Or instead of using 40-30. But 480 is I found it 40%. I've not experienced and I've not actually tried 50 or 60%, which I would like to do that. But sometimes when you have a few materials that you have to work with, I'd rather be conservative and just be a little bit lower so that I make sure that when I collect data set, the data set's gonna be okay. With all what I can say is that with all the sample I've used so far at 40% power, so at 40 watts, I have not experienced much crystal radiation damage at that power settings. That makes me like I say, okay, I'm working on it. Maybe 50 or 60 will work too. I don't know. I didn't try that yet.
Okay, so the next question, can the Synergy-R sample stage be cooled down? I'm assuming this is asking about if it's compatible with cryo devices like the CryoStream. Do you have a CryoStream on your system?
I have a CryoStream 1000, yes, the new one.
Yeah.
Yes, so that works pretty nicely. Yes.
Yeah. Okay.
That's how I was able. That's actually how I was able to get that phase transition with that sample number 3, because with the CryoStream you have a really nice way to control the cooling rate. Whereas I do have an old Oxford instrument. What's the name of this thing? This CryoJet, and that does not allow you to say, for instance, I want to cool from this to this in 10 hours. I can do that with CryoStream, but with a CryoJet I cannot do that at all. I have no control over the cooling rate at all. So if people want to definitely interested in phase transition, the CryoStream is definitely the way to go. Yeah,
I mean the CryoJet is no longer available.
No, I know. Yeah. Not a bad cooling system, but
yeah, I mean it filled a role, but the CryoStream had definitely had superior control and
absolutely.
So did you change the anode by yourself, and is it easy?
Yes, it's not. I'm really bad with my hands, so as I talked to you about that, I'm not a very handy person, but yes. So everything is done remotely. You get help from, in this case, I'm sure in Europe it's a bit different, but in the US, Harold Abraham, who is in charge of basically doing the remote help assistance, does that. So we're on the phone, we're on the video. It gives you the instruction, do it. Yeah, it was not that difficult. Removing the anode is not difficult. Putting it back is not difficult. The only thing that really is a bit more tricky, I would say, is the beam realignment. You want to make sure that, and you get assisted, but part of the beam realignment is a bit more tricky, especially when you change the anode. When you change just the filament, you would have to do a beam realignment, but it's not as bad, I would say, as removing and putting back the anode. The anode, I did the last time I done it was July 2023, so it's September now, so about a year. It's probably up to change it. I need to rebuild it, so I will probably send it back soon. but really not that difficult actually.
So this is an interesting question. So one of the loops that you've used is broken. What
Yes.
is there an advantage to doing this? And
Yes, because you can pick up if you have a very nice hand, which I have a good hands for that. You pick a tiny bit and you just like up. You can just pick some very small crystal that way and see them a little bit easier. I do that in a way sometimes like it depends on the type of crystals. If you have a plate that's stuck, generally the not broken loop is better. But if you have a tiny crystal, you can just mount right at the top of the tip, and that just works very nicely. On those, like it does a fork, so it's broken, and you can just pick one. It works fine.
Very nice.
Way better than the Mitogen. That's and there's no icing.
Okay, so last question. I mean, I'll maybe make my own comment to this after you've answered. But it seems no one loves the Cobra from Oxford. Why is that? Have you ever considered using the Cobra or buying the Cobra?
No. It's noisy, and actually, like I don't have direct experience, but I've heard from experience from the Navy, like the Naval Academy in Annapolis. They used to have that. They do have now a Synergy-R, but they used to have a broker system, and they had a Cobra, and the thing break down all the time. So you use a compressor to extract the nitrogen from the air, and that thing is going to break pretty fast. So you put a lot of strains on this. So if you are able to get like a liquid nitrogen source, do that, because that makes things much easier.
Yeah,
and it's also I think it's also noisy too.
Yeah, sure. My answer was simply going to be that it requires more maintenance than the liquid nitrogen-based systems. But yeah,
absolutely.
Okay, well, that's all of the questions. So just like to thank you again, Max, for joining us and for giving this lovely presentation.
Thanks, Fraser, for allowing me the time. It was very nice.
Yeah, no problem. And thank you to everyone who joined us, and we'll see you next time. Thank you. Bye-bye.
Thank you so much. Ciao, guys. Bye-bye.